Chapter 33, AC Circuits. Consider this. We know from Chapter 31 that one of the ways that we would generate electricity and power is by having a large magnet and having a coil with, in between those magnetic poles, and to actually turn that coil in that magnetic field. And when we do, the flux is going to change sinusoidally, and we will get a sinusoidal voltage and hence a sinusoidal current. That's the way we generate power in the United States. So basically we end up with a voltage that is varying sinusoidally. Hence is going positive, negative, positive, negative, positive, negative. And the current that results from that is also going sinusoidally as well. So it's going positive in one direction, negative in the other direction, positive, negative, and so forth. So it's going to vary between a maximum value and a sinusoidal way. The frequency that we use in the United States is 60 Hertz, which corresponds to an angular frequency, omega, of 2 pi times 60, or 377 radians per second. So in general, unless otherwise stated, we are using an omega that is equal to 377 radians per second. If we were in Europe, it would be 50 Hertz, which would be an omega of 100 pi, or 314 radians per second. Alright, so we have ourselves an AC generator giving us this voltage that is alternating back and forth. And if we were to connect that across a resistor, we would find that the voltage of the resistor, being the only circuit element, would have a voltage that varied in the same way. So the voltage across the resistor would equal V max sine omega t, and for that matter, the current to the resistor would be related to this voltage by being I max times resistance R sine omega t. So we can relate the maximum voltage to the maximum current through the resistor by an Ohm's law type relationship. The maximum voltage will equal the maximum current times the resistance, knowing all the while that both of them are changing sinusoidally with time. And likewise, we can go the other way around. We can say that the maximum current should equal the maximum voltage divided by the resistance, again realizing all the while that the current and the voltage are changing sinusoidally with time. Well, if we have this sinusoidal current, one that's going positive and negative, the average value of the current over one cycle should be 0, because we're going positive a certain amount, and then we're going negative the same amount. So we're going positive, negative. If we were to average that current over time, we would get an average current of 0. Well, there's a problem here, because if we had a resistor there, it is going to heat up. It is going to dissipate energy no matter what direction the current is going. If the current's going one direction like this, it's going to heat up, give off energy according to I squared R, energy per time, and we will lose energy. And if the current's going the other direction, same thing. The resistor will still heat up, and we will lose energy according to I squared R. So power is going to be dissipated regardless of the direction of the current. So this is a problem. If we have an average current of 0, but we have a finite power being dissipated, how do we deal with that, at least mathematically? Well, we need to find a way to represent this AC current in a positive sense, in a finite sense, where we can deal with power. So to think about this, we're going to take our AC current that's going positive, negative, and we're going to square it. So we're going to square the value of the current so that all the values that we have after that are going to be positive. Where it was positive and that square, that's still going to be positive. Where it went negative and we square that, that's going to now be a positive quantity. So we square everything in the current, and we're going to take the average value of that. So we'll square the current, take the average value, and we'll end up with something finite that represents the current, at least the squared current. Then we're feeling kind of guilty about squaring the current in the first place. And so once we square the current and average that, we're going to kind of mitigate our initial squaring by then taking the square root. We're still going to end up with something finite, not non-zero, that represents the current. Good. So what we're going to do is we're going to take the square root of the average value of the squared current. Square the current, get a positive value, average that, and then we're feeling guilty, so we're going to mitigate the fact that we squared things and then take the square root. And we'll have something that represents the current that possibly we could use to help us represent power. So we have the square root of the average of the squared current, which we call the root nice square. The root nice square. Now I think it's the root mean square. The root mean square. Mean meaning average. For a sinusoidal, we can show that if we square everything, we're going to end up with quantity that is bounded between 1 and 0. And the root mean square value will be equal to the maximum value of the current divided by the square root of 2, which is 0.707 times the maximum value. If it were not a sinusoidal function, if it were a sawtooth function, it would be something like the maximum value divided by the square root of 3. Or if it were other periodic functions, it would be different. But for the purposes of this course, we're only going to deal with sinusoidal functions because that's the way we generate our power anyway. So, for us, the root mean square value would be the maximum value divided by the square root of 2. We can prove that. We know the sine squared value is going to be bounded by 1 and 0 because the sine is bounded by 1 and negative 1. So when we square it, it's now going to be bounded between 0 and 1. And it's going to be symmetric about those two endpoints. So if I were to try to find the average of this sine squared bounded between 1 and 0, that average would simply be right in the middle at 1/2. And if I were to take the square root of 1/2, I would get 1 over the square root of 2. So our IRMS, which is the square root of the average value of the squared current, would be the maximum value times the square root of the average value of sine squared. But the average value of sine squared is 1/2. The square root of that is 1 over the square root of 2. So the root mean square value is the maximum value divided by the square root of 2. This is true for the current. The root mean square current is the maximum value of the current divided by the square root of 2, which is 0.707 I max. And also for the voltage. The root mean square voltage would be our maximum voltage of the signal divided by the square root of 2, 0.707 V max. When you use a meter to measure current or voltage on an AC circuit, it will give you root mean square values. It will not give you the average current. It will not give you the maximum value. It will give you the root mean square value. If you put a meter up to the wall socket and you measure the voltage coming out of the wall socket, you will measure 120 volts. That is root mean square. The actual voltage going through the wall socket, it has a maximum value of 170 volts, but when you take 0.707 times 170, you have 120 volts. So the meter gives you the root mean square, or RMS, value. With this, we can now deal with power. The average power dissipated is equal to the root mean square current squared times the resistance in the circuit. And this will always be our power dissipated in an AC circuit. because the resistance is the item in the circuit that is actually dissipating energy. Alternatively, we could say for sinusoidal signals, since the root mean square current is the maximum current divided by the square root of 2, the average power would be 1/2 the maximum current squared times the resistance. Let's try all this out in a circuit. An audio amplifier represented by an AC source and resistor shown delivers to the speaker alternating voltage at audio frequencies. If the source voltage has an amplitude of 15 volts and R is 8.2 ohms, and the speaker is equivalent to a resistance of 10.4 ohms, what time average power is transferred to it? Well, we need to find the root mean square current first, and we're given that the amplitude of the voltage is 15 volts, so we can find the root mean square voltage from that. The RMS voltage will be the maximum voltage, 15 volts, divided by the square root of 2, which will be 10.6 volts. Now, if we divide the RMS voltage by the total resistance of the circuit, which will be 8.2 plus 10.4 ohms, we have 10.6 volts over 18.6 ohms gives us an RMS current of 0.570 amps. And oftentimes you'll also write RMS below the amps, just to indicate that you are indeed looking at a root mean square current. So that is our current in the circuit. So the power delivered to the speaker will be the root mean square current squared times the resistance of the speaker. 0.570 amps squared times 10.4 ohms means that we are delivering 3.38 watts to the speaker. Alright, so that's how we would deal with a purely resistive circuit. But we are going to be adding other devices into our AC circuit, in particular inductors and capacitors. What happens if we have an inductor in an AC circuit? Well, we know from chapter 32 that the voltage across an inductor is proportional to the change in current per time. If the current's not changing, then there would be no voltage across an inductor. So if we had a DC current going in our circuit, that would never change. That's direct current, that's constant current, and hence the inductor would have basically no influence on that circuit. Whereas if we had a current that was changing a lot, then the inductor is going to have a lot of influence on that circuit because its voltage is proportional to the change in current per time. In particular, if we had a current going sinusoidally, and if it had a large angular frequency, omega, then it might be changing like this, which is changing quite rapidly, quite a lot, and hence that inductor will have a lot of influence on our circuit. Whereas if the angular frequency were small, it might be changing just a little bit like this, and that inductor might not have as much influence on our circuit. We can quantify this by what we call the inductive reactance. It's basically a measure of the inductor's opposition to the flow of current in your circuit. And it looks like this. The inductive reactance, which is chi sub L, or you might call it X sub L, is proportional to the inductance by the angular frequency. So it's also proportional to the angular frequency. When the angular frequency is high, the inductor has a lot of influence, a lot of opposition to the flow of current in that circuit. The units of inductive reactance, X sub L, is equal to radians per second times henries, and that turns out to be ohms. So the inductive reactance has the same units of ohms, and in a sense it's doing something similar to resistance. It is opposing the flow of current. Now if it's an inductor, the way it opposes the flow of current is that it actually stores energy in its magnetic field, and then later on it's going to give that energy back to the circuit. For a resistor, it simply dissipates energy. So both of them oppose the flow of current, but for an inductor, it's because it's storing energy and then giving it back. It's not dissipating energy. In the Ohm's law-like relationship, we can say that the maximum voltage across the inductor is related to the maximum current in the circuit times its inductive reactance. Kind of looks like V equals IR, but it's V equal I inductive reactance. And the RMS voltage in the inductor is equal to the RMS current times the inductive reactance. But these current and the voltages happen at different times. We know from chapter 32 that when we first close a switch in a DC circuit, the voltage appears on the inductor because the current is changing rapidly at that moment. And the current hasn't even begun to flow. So the voltage across the inductor comes before the current in the circuit. And in this case, there's going to be a 90-degree phase relationship between the two. Let's try a problem. In a purely inductive circuit, the inductance is 25 millihenries and the RMS voltage is 150 volts. Find the inductive reactance and root mean square current in the circuit if the frequency is 60 hertz. Well, if the frequency is 60 hertz, the angular frequency will be 2 pi times that, or 377 radians per second. If we know the angular frequency, we can calculate the inductive reactance. X of L is omega times L, 377 times 25 millihenries, 0.025 henries, gives us an inductive reactance of 9.43 ohms. That is our opposition to the flow of current in this particular purely inductive circuit. So our RMS current is equal to our RMS voltage divided by the inductive reactance. 150 volts divided by 9.43 ohms gives us a root mean square current of 15.9 amps root mean square. What about capacitors in an AC circuit? Well, we know from our study of capacitors that the voltage across a capacitor is related to the charge on the capacitor. V equals Q divided by C. So, we have to have charge on the capacitor before we have voltage, and before that capacitor presents an opposition to the flow of current in the circuit. Charge has to flow before we have voltage on the capacitor. So charge, the current, is charge per time. So we have to have a current flowing into the capacitor before we can establish a voltage on the capacitor. The current comes first and then the voltage follows. It's a 90-degree phase relationship as well, but in the opposite direction. So since we must have current, there's going to be a relationship between the angular frequency in the circuit and the capacitor as well. What would happen if the angular frequency were high? Well, the current would be doing this. It'd be coming along. It would start to charge up the capacitor, but then if the frequency reverses, then it'll discharge. And then it'll start to charge, and then it'll discharge. And it'll start to charge, and it'll discharge. If that angular frequency is high, then the capacitor never really will have a chance to charge up, and hence it is pretty insignificant in the circuit. If I'm going this, then reverse direction, I charge up and then reverse direction, it never has a chance. Whereas if the angular frequency were small, then the current would flow and charge up the capacitor, and then finally switch directions and discharge the capacitor, switch directions and charge up. And if the angular frequency is low, the capacitor has a chance to charge and presents an opposition to the flow of current in the circuit. We can express this as the capacitive reactance. Chi sub c, or if you will, x sub c, is equal to 1 over the angular frequency times the capacitance. And if we were to multiply 1 over radians per second times farads, we would get units of ohms. So the capacitive reactance is a measure of a capacitor's opposition to the flow of current in an AC circuit, and it also has units of ohms like resistance and like inductive reactance. The way that a capacitor opposes flow of current is that it stores energy in its electric field between its plates and then gives that energy back to the circuit. So it's not dissipating energy like a resistor, but it is opposing the flow of current by storing energy in its electric field and then giving it back. The maximum voltage can be related to the maximum current in the circuit in a capacitor by voltage of the capacitance maximum is equal to the maximum current times the capacitive reactance, and same thing for the RMS. The RMS voltage across capacitor is equal to the RMS current times the capacitive reactance, in an Ohm's law-like looking relationship. But again, we must note that the maximum current and the maximum voltage are not occurring at the same time. They are 90 degrees out of phase. The current comes first and then the voltage. So we have a problem with inductance and capacitance in an AC circuit as far as phase relationships. In an inductor, the voltage, which we might call the EMF, leads the current. The voltage comes first and then the current follows. We can remember that by using Eli, the Iceman. Eli meaning EMF, comes before current in an inductor. We can describe that as a positive phase of 90 degrees or pi over 2. Whereas in a capacitor, the current leads the EMF, the voltage. So the current comes before the voltage. We can describe that as a phase relationship of negative 90 degrees or negative pi over 2. So here's a mnemonic device to help you remember the phase relationships between the voltages in these devices and the current in the circuit. Eli, the Iceman. Well, that's a good memory device, but I have one of my own, which I call Val, the Iceman. It kind of works in a similar way. In the inductor, the volts comes before the amps. See where I'm going with this? In the inductor, the volts comes before the amps. That gives you Val. And we know that in the movie Top Gun, Val Kilmer was the Iceman. Too old? Yeah, maybe it's too old. Maybe you don't remember the movie Top Gun. Oh well. We want to put all these elements in one circuit. We want the resistance, inductance, capacitance, all in one series circuit. We have a problem though. If we run an AC current through this, the voltage drops across these three elements are going to be out of phase with one another. The resistance will be totally in phase with the source, but the voltage across the inductor will lead the current and the voltage across the capacitor will lag the current. How can we possibly add these voltages when they're totally out of phase with one another? That's a good question. Well, to do this, we are going to introduce a concept called phasors. Imagine this. We have a device where we can put this device into a handheld gun-looking mechanism and shoot a laser out one end, and we can set it to either kill or stun, and we can use this to take over the universe. No, that's phasors as in Star Trek form. Incidentally, this device would also be good for caulking your windows. It's a good caulking device for windows and doors and stuff like that. We want a different kind of phasor. We want a phasor that looks like this, where we have a vector, but the vector is not stationary. It is actually rotating at an angular frequency omega. And because of its rotation, its projection onto the y-axis will give us the magnitude of the vector times the sine of omega t at any particular time. So we can think of this as a vector that represents a signal, but then the sinusoidal aspect of it is this vector rotating with an angular frequency omega t. So the projection of this vector on the y-axis is the value of our signal at any particular time. So if we have the current, and that is a phasor, that's a moving vector, we would have a value for the current at any particular time, with the maximum value being the length of the vector. And then the resistance, the voltage across the resistor, is in phase with that vector, so the two vectors would move together as they're rotating with an angular frequency omega. Each vector's length will be its maximum value, and this rotating vector is called a phasor. So we can now think about what's happening in our circuit with these representations called phasors. For the resistor, we have a voltage across the resistor that's totally in phase with the current as the current is changing sinusoidally. But with the inductor, the voltage comes before the current. The voltage is always going to be 90 degrees ahead of the current. So as we go through this omega rotation, the voltage will maintain that phase relationship with regards to the current. And in a capacitor, the voltage lags the current. So as the current is coming around, the voltage will always be 90 degrees behind. So if we were to take a snapshot of this circuit with one current representing the circuit, we would have the voltage of the resistor in phase, the voltage of the inductor 90 degrees ahead, and the voltage of the capacitance 90 degrees behind that current. Well, if we were to add these voltages together vectorially, we could go ahead and subtract the voltage of the capacitor from the voltage of the inductor and get some net voltage in the y direction, and that will be perpendicular to the voltage of the resistor. So we can add these voltages together and then vectorially determine our maximum net voltage for this circuit. So we would have to square the components in the x direction, the voltage of the resistance, plus the net voltage in the y direction, square that, add them together, take the square root, and we'll get the value of our maximum voltage for the circuit. So it would look like this. Vmax is equal to VR squared plus our net reactance voltage squared, square root, which I could write as I max R squared plus I max inductive reactance minus I max capacitive reactance, that's squared. Let's factor out a I max out of everything. And we would have that V max is equal to current max square root of R squared plus chi sub L minus chi sub C, that quantity squared. Well, we now define what we call impedance, Z, to be equal to the square root of our resistance squared plus our net reactance squared, where our net reactance is equal to the inductive reactance minus the capacitive reactance. So it would look like this. We have resistance, we have a net reactance, which is x sub L minus x sub C, and if we square one plus square the other, take the square root, we get the impedance Z. And with this impedance definition, we have that our maximum voltage is equal to the maximum current times the impedance Z. Why do we use Z for impedance? Well, we could say that this is the last chapter of the second semester of physics, representing one full year of physics, Physics 1 and Physics 2. We're in the very last chapter, and we have finally made it through the alphabet. And so we're using Z as our last variable that we introduce. We made it through the alphabet, and there we have it. Our impedance is Z. That's my explanation, and I'm sticking to it. With this definition, we can now define the phase angle between our voltage and the current as being equal to phi, and that is equal to, as I look at this triangle here, the inverse tangent of our net reactance over our resistance. We can think of it as our imaginary portion of opposition to our real portion of opposition. Well, with this impedance, we can deal with a series RLC circuit, and the impedance, the total opposition to the flow of current, is equal to R squared plus a net reactance squared square root. This one equation, this one impedance, will help us deal with all the variable type of circuits that we wish to do in a series sense. So if we had an RL circuit, our capacitive reactance would be 0 because we have no capacitance there, and hence this X sub C would be 0. X sub L squared would simply be X sub L squared, and our impedance would be R squared plus X sub L squared square root. If we had no inductance, X sub L would be 0, and we would have a negative X sub C squared, which is this X sub C squared. Our impedance would simply be R squared plus X sub C squared square root. If we only had inductance, R would be 0, X sub C would be 0, we'd have X sub L squared square root, which is simply X sub L. So if we have only inductance, our impedance would be equal to the inductive reactance and would have units of ohms. The impedance has units of ohms. If we only had a capacitance, our impedance would be the capacitive reactance. And if we only had a resistance, our impedance would be the resistance. So this allows us, using this one formula for impedance, to deal with all these different types of circuits. Let's try this out. A series AC circuit contains the following components. R is equal to 150 ohms, L is equal to 250 millihenries, C is equal to 2 microfarads, and a generator operating with V max equal to 210 volts is operating at 50 hertz. Calculate the inductive reactance. Well, our frequency is 50 hertz, so our angular frequency is 2 pi times that, or 314 radians per second. It was also labeled up here. So that's our omega. Our inductive reactance is, by definition, omega times L. 314 times 250 millihenries gives us 78.5 ohms. So that is our inductive reactance, 78.5 ohms. What's the capacitive reactance? Well, that's going to be 1 over omega times C, 1 over 314 times 2 microfarads, and 1 over that gives us 1592 ohms. So right off the bat, I can say that this particular circuit is more capacitive than it is inductive, because the capacitive reactance is greater than the inductive reactance. The net reactance is the inductive reactance minus the capacitive reactance, which will give us a negative 1,514 ohms. And the fact that the net reactance is negative also means that this circuit is more capacitive than it is inductive. So what's the impedance? The impedance is the resistance squared plus the net reactance squared, square root. And that's going to be 150 ohms squared plus a negative 1514 squared, but that negative squared will be a positive value. So it's going to be 1514 squared, square root. Or our impedance is going to be 1,521 ohms. What's the maximum current? That would be our maximum voltage divided by the impedance. So that would be 210 volts divided by 1,521 ohms, 0.138 amps. If I wanted the RMS current, I could take this maximum current and divide it by the square root of 2. What's the phase angle? That's the inverse tangent of the net reactance over the resistance. So that would be inverse tangent of negative 1,514 over 150. Ohms cancel out. That'll give us a negative 84.3 degrees, and we can see that this particular circuit is very nearly totally capacitive, because a negative 90 would have given us a fully capacitive circuit. That concludes the first lecture in Chapter 33, RLC circuits. Try your hand at the problems in the problem set. This gives you a basis for attacking RLC circuits involving any of those components. So you have a lot of tools to attack those kinds of circuits.